All right, we're going to be finishing off this chapter, this section 10.6, with an application problem involving exponential decay. And so let's check out this bad boy right here. It's a lot of our same functionalities that we've been doing with the previous examples. This is just in the context of this problem, but we're not going to be doing any new math that we've been doing in this section here. So we have this radium 226 decays according to this gnarly looking function right here. F of t equals y naught e to the power of negative 0.00043 t. Alrighty, the y naught just means your initial substance, and then F of t will represent the amount after it decays, and the t means your time, of course, there. So what we want to know here is if an initial sample contains 4.5 grams of this radium 226, how many grams to the nearest tenth will be present after 150 years? It just sits there. We don't have any other information about weathering and all the other kind of elements, but what would you get, right? So all we can basically do is just kind of plug it all in right here. So we know that our T right here is going to be 150, right? They tell us that our initial value is 4.5 grams. And that's pretty much all we need to know. We just plug this in, and then we use the calculator to give us like how many grams that we're going to have. So let's just do it. So F of 150 is going to be equal to our initial 4.5 grams times e to the power of negative 0.00043 times 100. Sweet. So that's the exact answer. It's not very helpful to us. So let's go ahead and find an actual answer here. Plug that bad boy into our graphing calculator. So let's do that there. So we'll do 4.5 times e to the power of negative 0.00043 times that by 150. And which means that how many grams are we going to have left? We're going to have 4.22 grams, or I guess to the nearest tenth. So we'll have 4.2 grams left. After only 150 years? That's right. Not much left over, right? Or, I mean, it didn't really decay all that much, so that's how much we're going to have left over. So that's for part A. And then for part B now, what is the half-life of this of radium 226? So like, how long is it going to take for this to actually cut in half? We'll see hundreds, thousands, millions of years. We'll find out now. So we can use the same formula right here. Again, we'll do a different color. Our time is what we don't know, right? So that's what we're going to be looking for. We know what the initial value is. It's 4.5. But we also know what f of t is, right? F of t, it needs to be half of 4.5, because we want to know like how long is it going to take to be like half of that substance. So what's that? 2.25. Okay, so we can go ahead and plug in what we know, and then we're going to try to figure out what our time is here. Okay, so let's do that right here. So 2.25 is equal to 4.5 times e 43t. Great, so I'm going to go ahead and first divide by 4.5, and you're going to see that these are the exact same steps that we've been doing in previous problems that look just like this. That's half of that. E to the negative 0.00043t. Okay, notice again that when we have e as our base right here, then we're going to go ahead and take the natural log of both sides, because we know that that's going to cancel out. So let's go ahead and do that then. So we're going to take the natural log of a half on the left side, and then we'll take the natural log of the right side. According to our power rule, this thing can come on down in front. So the ln of a half is equal to now negative 0.00043t times our ln of e, and we like the ln of e because that's just 1. This is just 1 right here, so we're left with just this guy then. ln of a half equals negative 0.00043t. Cool beans. Just about done there, so now we can divide by this bad boy, and we'll be good. The answer is ln of a half all over negative 0.00043. That's what we're looking for. But again, when we talk about time in years, normally we don't use ln, so we can go ahead and just convert that into time. So bust that into your calculator, and you'll get 1,612 years. All right, and there we go.